It's time for the last part of Chapter 1. It's really easy, so this shouldn't take long at all. A composite function is a function that combines two or more functions, where the image of the first function is used as the object to the second. Composite functions make it more convenient for us by shortening two different operations into one. So instead of inputting 1 into the function f to get a, and then inputting a into g to get alpha, we put 1 into the composite function g of x to yield alpha immediately. Here are some examples of composite function notation: g f of x, f of x, h f g of x, and g squared x. Basically, this means applying the function g on the image fx. When you evaluate composite functions, always start with the function closest to x. So, for h f g x, you evaluate g of x, then plug it into f, and then plug fg of x into h. The important thing to remember is that the order in which the functions are written matter. An easy example to illustrate composite functions is the following. Imagine you're starting off at a job away from home and you're looking to rent this apartment. How much would you have to pay? First, you'd have to calculate the area of the apartment. Then, you'd multiply the area with the rent per square foot per month to find out the total amount you'd have to pay in rent every month. Let's work it out step by step. For simplicity, let's assume that the apartment is square, so its area A is a function f of its length x, which is x squared. Then given that we know A, we can calculate the total rent per month, R, by multiplying A by the rent per square foot per month of the apartment. A typical rent per square foot of a single-bed apartment in Kuala Lumpur is roughly 3 ringgit as of 2018, so let's just multiply A by 3. So suppose our apartment is 25 feet long. This gives us an area of 25 squared, which is 625, and thus a total rent of 1,875 ringgit a month. As you can see, we required 2 steps of calculation to get to this result. But composite functions can help us do it in half the time. Here's how. Since r is a function of a, and a is a function of x, we can just substitute f of x into the function g to get 3x squared. So suppose x is 25 again, we can just calculate our rent immediately with gf of x to get the same 1,875 ringgit. 1,875 is pretty high considering that 50% of KLites earn below 4,500 ringgit a month, almost half their salary in fact. For your general knowledge, a rule of thumb is that you should be spending about a third of your salary on housing. This makes housing one of the biggest expenses in our lifetimes. That's why our finances and where you choose to live are factored in heavily when you make these decisions. We just completed an example of a composite function that helped us calculate in one step the total rent per month based on the square-shaped apartment's length. Just think of it like making a burger. Starting with some meat, you've got to grind, season, shape, and grill it to make a finished patty. But then your patty is then used as a component to make the overall burger. In the exams, you'll sometimes be asked about combinations of inverse and composite functions. When approaching these types of questions, be mindful of the brackets, because they tell us which part of the composite function is being inversed. Here is another illustrative example of this being used in real life. Peter is 25 years old, 170 centimeters tall, but is overweight, and currently has a body mass index, or BMI, of 30. He knows that although frequent exercise helps you reduce weight, you can never outrun a bad diet. Therefore, he aspires to reduce his BMI to a healthy level of 22 by reducing his daily calorie intake. How much does he need to reduce it by? Note here that a calorie is a general unit for energy. If you use more calories in your daily activities than you consume through your diet, you lose weight, and if you eat more than you use up, you gain weight. Let f be the function that gives Peter's BMI based on his mass, assuming that his age and height are constant, and g be the function that gives the reduction in daily caloric intake over 1 year. This formula simply takes the difference between Peter's current weight and his BMI target weight, multiplies it by 7,700 calories, which is the calorie reduction needed per kg of body mass, and then dividing it over a period of 365 days to get the required daily reduction. How would you use concepts of inverse functions and composite functions to perform this calculation? Pause the video to think of a strategy yourself. Are you ready for the answer? One possible approach is to calculate Peter's ideal mass based on his target BMI by taking the F-inverse function. Then, we can use this as our input to the function g, which tells us how much he needs to reduce his daily intake by in order to lose m kilos. Putting both of these together in the function g F-inverse of p, we can get a function which calculates the number of calories Peter has to reduce daily in order to achieve any BMI p. So we can input p equals 22 to get the answer that Peter needs to reduce his daily intake by 487 calories over the course of a year. That concludes my explanation for this video. Do note that for illustrative purposes, I have used simplifications in both the rental and BMI example, while keeping only the essence of these problems. You are bound to have to solve them someday, so why don't you Google them and find out more? I've included some helpful links in the description to help you get started. That's all for this video. Remember to stay curious and always follow your dreams. See you in my next video.